I think this is a good one to do. Yeah, let's do the night student one. So this is number 9. Now, when you might have a slightly different version of this. It's either going to say the mean GPA of night students is greater, or the mean GPA of night students is smaller or significantly different. So you may get a left tail, a right tail, or a two tail on this problem. So this is one I'd recommend doing more than once if you wish. And the computer will remember your high score. So don't worry about redoing it and getting it wrong if it's a slightly harder version. So mine is significantly different. I'm glad to see that because that makes it a little harder. And then I have the data here, but I also made the calculations for you. So I calculated X bar and I calculated S. Since I have the data, I could use stat key. Stat key only works if you have the data. If somebody just says, hey, here's the mean and the standard deviation, stat key, that's not enough information for stat key to do a hypothesis test. Using the simulations we did before. Okay, so what do we got going on here? We're testing a claim. Okay, hypothesis test. Mean GPA. Okay, mean. So when we consider our branching of what we know so far about statistics, we're in the hypothesis test section and we're in a mean. So the question is, do we know the standard deviation of the population or we don't? And usually it's in the I don't know category. And then also, if you have a small sample size, I should add that here too. So small, come on, pen. There you go. Or, you don't know, I should say and or. Okie dokie. So back to that new page. And then I'm just going to copy all of this into my notebook. On paper, don't write those numbers down, okay? You may copy them into a spreadsheet, and I'll do that in a sec too. So I'm just going to take a screenshot of that much and run through how to do this on a spreadsheet. All right, so according to my cheat sheet flow chart there, I have, let's see, how many people? 40. Okay, that's not small, but anywhere in here, do you see the standard deviation of the population is blah, blah, blah. So let's read it again. Test a claim that the mean GPA of night students is significantly different than 2.8 at the 5% significance level. And they say, pick the hypotheses. Is it left, right, or two-tailed? And then there's 40 people here with a mean of 2.914 and a standard deviation of 0.096. Nowhere here does it say anything about the standard deviation of the population, which even though the sample size is greater than 30, I have to use a t-distribution. Okay, so right away, I have, oops, pen, I have no population STD, right? So that means, again, sigma not known. It did not come out right. There we go. Which means I have to use a t-distribution. All right. So I got to use a t-distribution here. So to use a t-distribution, you need to take the data and turn it into a t-score. So find t, that's supposed to be a t-score. And a t-score is like a z-score. Remember, a z-score is the number minus the mean over the standard deviation. So in this case, the t-score is going to be our mean, so x bar, minus the population mean, that's given up here. And then you want to divide that by parentheses, the standard error, and that would be S over the square root of N. And that's not very good, S, a little better. Okay, so like a z-score, this is a t-score, and notice it's got x bar minus mu, which we've done before for z-scores, but we just, instead of dividing by sigma because we don't know it, we divide by S over the square root of N because we're doing a hypothesis test. So for me, that means I need to take that 2.914 minus the questionable population number there, 2.8, and then divide by, I was given, divide by the sample standard deviation, 0.096 over the square root of 40. And all of these parentheses are necessary here in between. So sometimes this is written stacked, but I like it not stacked because that's the way it goes on calculators. Okay, so other things. I need to identify hypotheses, so let's think about this for a minute. Test the claim that the mean GPA of night students is significantly different. Okay, so different means not the same, not equal. So this sentence up here, translated into English, says mean, mu, significantly different, not equal, 2.8. Now, since this has a not equal in it, this must be the alternative hypothesis. So let's highlight that. And this is something we all struggled with, identifying which one is the null hypothesis and which one is the alternative. And the trick is to analyze the English of the claims you were given. If one of them has an equal sign in it, it has to be the null. If it doesn't have an equal sign, and this is a not equal, so that counts as a that's not an equal sign, it's not equal, then it's the alternative. So which one of these here has an alternative that is mu not equal to 2.8? And for me, it's this one. Now yours might have said, test the claim that the mean GPA of night students is more than 2.8, okay? So if yours had instead, so let's go down here and suppose yours said more than, and maybe it wasn't 2.8, maybe it was like 3.1, then that would translate in English as mu is greater than 3.1. Since there is not an equal in that statement right there, this would have to be the alternative, okay? And then there's a couple of options for the null. The null would either be equal to or less than or equal to. And different people take different poses on that based on the situation. So this one right here is the only one that works for me. So I would check that box right there. And since it's a not equal to, that is a two-tailed test, which makes my p-value a little bit more complicated. And then if I wanted to, I could enter this data into a spreadsheet to confirm these numbers, but I was already given them, so I don't need to recalculate them. I trust that they were calculated correctly, but if you don't trust that, feel free to redo it. All right, so I need to make that calculation. That gives me my t-score. And so what's the point of the t-score? Why do I find that? So I'm going to draw y here. And StatKey kind of did this automatically for us before. So this axis here is for my t-scores, not the actual numbers in the GPA, but I'll fill them in a minute anyway. The middle for t's like z's is always 0. I need to calculate this number. Since the sample is bigger than what was expected here, this is going to be a positive value. So make a quick note of this, 2.914, 2.8, 0.096. All right, I got to type all that into a calculator. Actually, spreadsheet would be the way to go here. Let's put this in a spreadsheet, new tab, and I'll label that later. Might as well grab the data while I'm here. When I should have started a new video for this. I guess I'll split them later. This is night school. Oops, missed a letter. GPA and paste. And then underneath here, I'll get the sample information just to double check. N equals X bar, sample mean equals, and then S equals. So count. Yeah. Oh, I'm still online. I'm sorry about that. All right, so there's my count, average, and std, oops, equals std s sample. And if I round those should be the same numbers I was given. 2.914, 0.096, yep. And I don't need that many decimal places visible. Okay, and these are 3 decimal place values because the data was 2 decimal places, the way I chose to round them that way. All right, so then I need, so that's from the sample. Next is sampling dist. And this is a t-dist. So I need the t-score, which is often called the test statistic. Test statistic, as opposed to the sample statistic. So the sample statistic is the X bar. And then I also have information about the population, right? Population, like the null hypothesis, that would be called the mu. And there is a way to get the symbol mu in there, but I'm too lazy to do it today. Mu is given as what for mine? I think it was 2.8. And that's all they gave me about the population. So this is also my null hypothesis too. Okay, so let's calculate that test statistic. So I said use parentheses when you do this. So parentheses take the sample mean minus the population mean, divide by another parentheses to get the standard error. And so that's going to be S over the SQRT of the sample size. Close the square root, close the denominator, and Google is better at guessing at your parentheses. If you don't put them in the right spot, Excel just flips out on you and says error. So make sure you end stuff in the right spot. I think that's good. I get 7.48 for the t-score. Whoa, that's huge. Think about z-scores. A z-score of 3 is pretty big. So that's gigantic. Wow, make a note. Okay, so my drawing. So normally with a t-scores are a little wider than a normal t-distributions are a little wider. So with a normal distribution, we usually go like 1, 2, 3 standard deviations are about here. T-distribution spreads out more than that. So it's going to be more like 1, 2, 3, 4. And t-distribution's width depends on how many numbers are in the sample. So the more numbers, the narrower it is, the fewer numbers in the sample, the wider it is. So my guess is that 7, a t-score of 7 is way out here in the fringe. So 4, 5, 6, I'm thinking this is 7 for a t-score out there. And then we want to calculate that tail probability. I mean, that's going to be like my p-value, my guess here, since 7 is so far from 0 for standard deviations, I'm going to think the p-value is going to be about 0. So to calculate the p-value, we needed this t-score right there. I showed last week how to calculate kind of a p-value with the norm.dist. So here we're going to use, I think it's called the t.dist. I better look that up on my spreadsheet. So after I get the test statistic, I'm ready to find the p-value. And that should be t. There's no t.dist. Oh, there we go. T.dist. I think I want this one right here. Left-tailed students t-dist. Left-tailed. What's this? The two-tailed students t-dist, or the right tail. Okay, my number is positive is to the right. I'm going to go for the right tail. I'll try the two-tail in a minute too, just for fun. Okay, I want to know what's your X value, and X is the input, which has to be a t-score. So my t-score is above, comma, and then degrees of freedom is always 1 less than the sample size. And I wish they would say that here, but they don't. So that's going to be an n minus 1. So here's n up here, minus 1. And then enter. Ooh, that's a wicked, it's almost 0. Look at that's wicked tiny. I can't even count all those zeros. Let's copy that. And can I paste it in here? So let me see, what did I type? I typed T dot, that's a funky T, try again, Gary. T dot dist dot right tail. I think it was just an RT maybe. Is that true? Yep. And it wants to know what is your t-score, which is this calculation there, comma, what's n minus 1. And mine was, can I paste it in here? Yes, this wicked small number there. All right, so I was guessing it was about 0 because I thought a z-score, again, is like a t-score. Usually data is within like 3 standard deviations, maybe 2. We're at 7. Now, this is a two-tailed test, right? So whatever happens out here, I have to reflect to the other side because this is, again, a two-tailed test. We have double tails. And most people had trouble with this way back when we were doing these hypothesis tests because they say they forgot their other tail that they're supposed to mirror out here. So that would have to go with a value of -7. T-distributions like a normal dist are symmetric. So my p-value is actually 2 times this because it's a two-tailed test. So fix my spreadsheet. So to calculate my p-value here, I actually have to go back here in my formula and multiply it by 2. Okay, but it's still wicked small. It's like 0. So if somebody said, hey, what is it to 3 decimal places? It's 0. What's it to 4 decimal places? It's 0. What's it to 5 decimal places? 0, 6, 0. It's 0. There's such a remote chance of this happening. What does that mean? All right, so this number has to be times 2, which is still about 0 to 3, 4, 5, 6, 7 decimal places. Help. There we go. So back here, what's my p-value to 2 decimal places? 0. All right, what does that mean? So if you get a tiny p-value, that means there's something wrong with the null hypothesis. And the null hypothesis says night students have a GPA of 2.8. We think it's different. Now our sample says it's bigger. Okay, but that wasn't our alternative hypothesis. Our alternative hypothesis is different. So my conclusion would be there's sufficient evidence that the GPA of night students is not 2.8 on average. It's something else. Okay. So that's 0. We're rejecting the null hypothesis. And I didn't ask for a conclusion here, just the decision. Ta-da, and we did it. Whew.